Hi everyone, I'm Kostin, software engineer here at Voltz Labs. Prior to this, I studied computer science at University of Cambridge and worked as developer at Meta. Today, we're going to give an overview on how to build on Voltz protocol. This guide consists of three parts. The first part is explaining the general concepts and the key user flows. The second part is how to execute these flows on-chain via the Voltz Periphery smart contracts and off-chain via our newly improved SDK. And last but not least, Alex and Sol will emphasize on how these were used in our recent integration with Mellow protocol. So I'll first let them introduce themselves and then continue with the presentation.
Hey, I'm Alex, and I'm a software engineer at Voltz, joining the team just after graduating from the University of Cambridge. And before that, I've also completed 2 internships at Google.
Hi, I'm Sol. I studied at Cambridge and Imperial College, and I was a software engineer at Accenture Liquid Studio. And now I'm a software engineer here with Alex and Kostin at Voltz.
So yeah, let's start with with the agenda for today. This is about, again, in the beginning, talking about general concepts and then emphasizing on the integration with Mellow in two different parts of the stack. First, when it comes to developing the Voltz Vault, and then once we have these Voltz, the strategy that orchestrates the Voltz Vaults. So first, Voltz is a protocol that launches pools on top of variable markets, and the two main actors are the liquidity providers and the traders. Each pool has two underlying smart contracts, one VMM used for price discovery only, and a margin engine that keeps track of all positions, cash flows, and margin thresholds, given that the protocol allows leverage on all positions. So when it comes to building on top of Voltz, you need to interact with the VMM and the margin engine if you want to interact with the pool. Voltz, in order to facilitate these interactions, deploys a periphery that synthesizes and facilitates these integrations with the underlying pools. First, we'll go through all the key user flows, and then we'll see how to interact with the periphery if we want to interact on chain, or with our SDK if we want to interact off chain. So the main flows on each pool are the following. Either you mint or provide liquidity. As I said, like one of the main actors are the liquidity providers that do one or two, mint or burn liquidity. Then the third one is for traders, where you can trade rates, either taking the fixed side or the variable side of the market. Then another user flow is where you deposit extra margin in order to collateralize your position more, or when you withdraw your margin when you want to increase your leverage. Then 5 is where you can liquidate another position. So in order to keep the protocol safe, users can liquidate positions that are in the danger zone, that are at risk of becoming insolvent. Then the sixth flow is when these pools matures because they have fixed term. When the pool matures, you can settle your position, and the cash flow is calculated, and you can withdraw all your cash flow and the margin you deposited in order to collateralize your position, or withdraw less margin because you are in a loss in a losing position. So and the seventh is when once you mint or trade, then what you end up with is a position that you might need to track in order to deposit margin, in order to withdraw more margin, so you can add it on the way. Right. For the sake of this guide, we focus on the first flow, on the mint or provide liquidity, and we analyze how we can activate this flow both on chain via the periphery and off chain via the SDK. So let's go to this example. First, we'll analyze on chain, and we'll go into our Voltz core repo, into this function in the periphery, in the smart contracts written in Solidity, where we can see that mint or burn accepts some parameters, and we'll understand what these parameters are. First is the margin engine address. As we said, each pool has a unique margin engine and a VMM. So here, if we specify the margin engine address, it means that we specify what pool we're trying to mint on. Then tick lower and tick upper. These are the ranges, because our pool works on a concentrated AMM. You can concentrate your liquidity into ranges. So tick lower and tick upper are some smart contract formats of these fixed rates. Then the amount of notional, given that the protocol allows leverage, this notional is synthetic. So for example, if you want to mint 1,000 USDC liquidity on a AUSDC pool, let's say, you specify 1,000 in this notional, and then if you want to take 100x leverage, you can deposit just 10 USDC as margin. And this flag is mint is obviously true because we provide liquidity at this point. Right. So this is how you. This is the place where you interact with the smart contract. And if we go back to the presentation, here is an example on how we can provide 1,000 USDC between 0.9 and 1.2% on the AUSDC pool. So first, you see that we connect to our periphery, which you can find in the documentation on voltz.xyz. This is the margin engine address of the AUSDC pool. This is the scale notional by 10 to 16 because it's USDC. Here is tick lower and tick upper. You can see the conversion also in the docs between ticks and fixed rates. It's a one-to-one conversion. So this actually represents 0.9 and 1.2%. Mint is true, as we discussed, and margin delta is 10 because we decide to take 100x leverage on this position. Then, if so this is the interaction on chain directly with smart contract. If we want to do this off chain, we have support in the new SDK for this, and here is an example. If we first look into our SDK, we have this utility called get AMM in here. Essentially, you specify a string, which is the VMM address. So you see that this uniquely identifies the pool via VMM address. Then you just provide a signer and the provider. So the provider can be an Alchemy endpoint or so, and the signer can be your wallet, or just your address if you want to use this object for read only. And we see that we receive a fully initialized AMM object. If we look into this AMM object, it has a functionality called minterburn. Here specified that it will do a smart contract call. So we see that these are the arguments, and we'll see here in this file that the arguments in the SDK are more in human readable rather than ticks, scaled numbers, and so on. So here we just provide this flag is mint as true, then notional as just 1000, fixed low and fixed high 0.9 and 1.2, so you don't deal with any conversions, and the margin just as 10 because you take 100x leverage. Right. If we and also in this SDK you have tracking position tools. For example, you have an object class, a position class. Sorry, as we have AMM class. That position can be instantiated with the ticks you use and the address, and then you can track the position health. You can find more details in the article. Right. So if we go back to our slides, here is an example of how to do this liquidity provision off-chain using our AMM object. So first we need a provider. So yeah, you just need an RKM endpoint. Then you instantiate a wallet. So you pass your private key and then you connect to the provider. Then you initialize this class. First you provide the VMM address, the provider and the signer, and then you just wait for this class to happen. And we see that here the arguments are in more readable format. Right, so this is on the integration, and now I'll let Alex introduce how we used these iterations for this time on-chain when integrated with Mellow protocol.
Thank you, Costin. Yeah, so now I'm going to jump into our integration with the Mellow protocol. We'll first show you what that is and then how it was built. So first, let me show you where you can find this integration on our website. So if you go into our main app, so app.voltz.xyz, you can go under the liquidity providers and under the LP optimizer section. So in here, you'll be able to see multiple cards. Each of these cards will represent a vault that was built with the Mellow protocol, which basically aggregates multiple pools that are deployed on Voltz protocol. So for example, this Mellow ETH card here shows you that you can provide liquidity, and that will be spread across these 4 pools that are currently live on our app. Basically this is what we built with Mellow, and now I'm going to show you how we did this to give you a better understanding of how to integrate with Voltz. So going back to the slides, first I'm going to talk about the Voltz Vault, which is the main connection between our protocol and Mellow, and then Sol will talk about the strategy, which basically decides what is the best position to provide liquidity and so on. For now, we're just focusing on the Vault, which from the perspective of Voltz is just an LP. So Voltz Vault is of course a smart contract in this case. However, from the perspective of the protocol, Voltz Vault is just an LP. And this Voltz Vault So there's one Volt per pool. So basically it has one associated margin engine and then one associated VMM. And the Vault will receive the user funds, and the Vault is also responsible for minting the right amount of liquidity on Vaults in the optimal tick range. So again, the strategy is the one which handles the optimal tick range. The Vault is just responsible for like minting the liquidity. So we'll analyze two main flows within this Vault. The first one is the user deposit, and the user deposit is constructed of two parts. The first one is that funds that enter the Vault must be pushed as margin in the optimal position. So we need to initiate a position on Vault and push the funds as margin. And then we need to mint liquidity in the optimal position as instructed by the strategy as I've told you before. Basically the liquidity, the notional minted is computed by multiplying the margin by the leverage as shown earlier by Kostin. So now I want to show you how we did this in the code. So in here we have the Voltz Vault contract. If I show you the push function, so this is the function that is called whenever funds are entering the Vault. And you can ignore other details from here, but the two main points that we need to understand is update margin and then mint or burn. So basically this corresponds to these two parts right here. So the first one is we need to push the margin, right? So this is the one responsible for it. We get the current position, the optimal position, and then the funds that enter the Vault, and then we need to update the margin of that position. So if we go into this helper function, we'll see that what it does, it takes the periphery of the pool, and then it just calls the update position margin function. So first we need to pass the margin engine of the pool. So the periphery is one per the protocol, right? The margin engine and the VMM are per pool. So we pass the margin engine of the pool, and then the lower and upper ticks of our position, and then the margin delta. So this in here must be positive. This would signal deposit. And then here, this false parameter just means that we don't want to withdraw like the margin. So this only means this is only used if we want to withdraw all the margin. For now, this is not used here. So basically, this is all that we need to do to update the margin of the position. And if we go back to our push function, this is the update margin, as I said, and now we need to look into how to mint the liquidity. So this is the second step right here. So we need to mint notional that is equal to margin times the leverage. So we first compute the notional that we want to mint. So this is, as I said, tokens, so the funds that enter times leverage. And now we have this function. So first, the first step here is to transform the notional that we want to mint into liquidity, because the smart contract level, there's no, the smart contract works with liquidity rather than notional. So for this matter, we have this function here. So get liquidity from notional, which just calls a function with the same name, get liquidity for notional, on the periphery. And then what we need to do here is just to pass the notional amount and then the lower and upper ticks in square root prices. So in order to convert the lower and upper ticks to this format, you can just call this function on the tick math contract, which is also part of our core repository. All right, so once we have this liquidity amount, we can go into the mint or burn liquidity function here, which in this case, unlike shown previously, we don't mint or burn through the periphery, but rather directly on the VMM. So of course, you can choose either of these two options. You can either choose use the periphery, which provides a more high level usage of this, or you can directly interact with the VMM and margin engines. In this case, we interact directly with the VMM, and then we mint the liquidity. So we pass the address of the owner of the position, which in this case is the address of the vault, the lower and upper ticks, and the liquidity that we've just computed. And basically, this is all that we need to do to basically accomplish this first main flow of the vault, user deposit. Now let's move to the second flow. All right, so the second main flow of the vault is the change in optimal position. So let's say there's been some movement of the market, and now there is another optimal position where we should put our liquidity in. Of course, for like upcoming deposits, this is easy. We just use this deposition to do exactly the same steps as we've done here. However, the challenging part here is to move the existing liquidity that was put in the old position to this new optimal position. And for this, we need to do two main parts. The first one is exit the previous position. This involves burning the liquidity that we've minted, unwinding the existing position, and then withdrawing the margin. And then for the second part, we need to deposit the margin and minted liquidity in the new position, exactly as we've done here. So let's see this first part, how this was achieved in the code. So if we go to the rebalance function, this will be called by the strategy as described by Sol just after this. So the rebalance function, again, we can ignore the details here. We are just interested in the interactions with the protocol. So first, we need to burn liquidity. We just use the same function as before, and we can just burn the liquidity that we've minted, right? Then, so this was the first part, the point A here. Then point B, we need to unwind existing position. So what this means is that unless the LP position was netted out perfectly by the swaps, there might the LP might act as a fixed or variable taker, which means that it has some variability with it, and we need to unwind it to get rid of that. And to do that, we need to make a swap to make an unwind, which basically means a swap that will cancel out all of the variable tokens accumulated by the position. So yeah, if we browse to this function, you can see that in here, we first check if the variable tokens are different than 0, and then if that's the case, if the position was not netted out perfectly, then what we need to do is we need to perform a swap with these parameters. So again, here we perform this swap on the VMM, but you can do this on the periphery as well. For the swap function, we pass the owner of the owner of the position, which is the vault, and then for the notional, we need to pass the amount of variable tokens because we need to receive negative of that so that we can cancel it out. So this is why here in the amount specified, we want to perform a swap with this amount, and then we pass these lower and upper ticks. And also there's this limit if you want to limit your swap with let's say a price. However, here we are not limiting at all. We are using the min and max values. You can find more information about this in our docs. So this is the part where we unwind the position, basically completing point B here. And then finally, for this part, we need to withdraw the margin. And to withdraw the margin, we first need to understand how much margin we need to keep in the position. That is because after this unwind, the position might still have some fixed tokens for which the margin engine accounts for. So basically, we need to understand how much margin must be left in the position. So if we go down here, you'll see this get margin to keep. And if we look into this function, this is a helper function. We're calling this get position margin requirement. This just gives gives us the margin requirement of the that is given by the margin engine for this position. So we need to pass the owner of the position and then the lower and upper ticks. And here the false parameter means that we are interested in the initial requirement rather than in the liquidation one. We are not interested in liquidations here. We're only interested in the initial margin requirement. So once we get this, basically we need to leave this amount plus one. Because we need to leave strictly greater, a margin that's strictly greater than that. And then once we have this value, we can return to this function and we can withdraw the difference, right? We can withdraw what is in the position, so the margin of the position minus what we have to keep in the position. And we also put this minus sign here so that we can signal a withdraw. And this function I've already showed you previously, but just to make sure, is just the update position margin function on the periphery, and this time with a negative margin delta. And also one note here, we have the margin of the position. This can be extracted from this function. I'll show you quickly. So I think it's here. Yeah, so we have this get position function on the margin engine, which will give you information. This is the seventh flow, the tracking position from earlier. This will give you information about the position and also the margin. Cool. So basically, this is how, and at this point, we've exited the previous position. And if we go back to the rebalance function, at this point, all that we need to do is follow the second step here, which is deposit the new margin and mean liquidity in the new position. So this is what to do here. We take the balance of the vault after this unwind, and then we put that margin into the new position and mint liquidity according to the leverage. So here again, we multiply the balance times the leverage. And then this is all that we need to do. So again, here, these interactions are the same as previously. All right, so this was a high-level overview of how to interact with the protocol. And of course, you can find more details into the article that is accompanying this video. In the article, we've gone into a bit more detail about how all of these flows work in the vault. Now I'm going to pass over to Sol to talk about how the strategy interacts with the vault.
Thank you, Alex, for explaining the Voltz Vault functionalities. Let's now talk about the LP optimizer strategy, which it is effectively a smart contract which lives in the Mellow ecosystem to manage liquidity vaults, such as the Voltz Vault that Alex was just talking about. What we've described so far, what Alex has described so far, is the Voltz Vault, which you can see here, or one of them at least. And Kostin was talking about the periphery and explaining the different interactions that it had with the margin engine and the VMM. So each of these flows in this diagram, it represents a sort of one type of Voltz Vault. Currently, I'm showing 4 Voltz Vaults, and where the optimizer strategy, the smart contract, lives is sort of here at the integration layer. Now, the strategy, it controls something known as a vault system, and a vault system is made up of an ERC root vault, an ERC 20 vault, and a Voltz vault, or also a sub vault. Now, this sub vault could be any different protocol. It could be Aave or Uniswap, and now it is also possible to have Voltz vaults as your sub vaults. A strategy, in effect, will implement any trading strategies that you may want to manage your liquidity, And one of the reasons we have implemented it is because the strategy is taking advantage of the Uniswap v3 mechanism, where any time your capital or liquidity goes out of range, or the range that you specified when depositing that liquidity, let's say between 1.9 and 2.1%, then that capital becomes inactive. And the strategy is effectively take your capital back out of that range and put it into the active range around the current fixed rate, or as a function of the current fixed rate. And that is the point of the strategy. The contract itself has two main roles. The first one is to check whether the current position, which is held in the Voltz Vault, any one of these, by a depositor, is still in the active range. And the second function is, if it is not in the range anymore, then it rebalances the position. It computes, or rather it computes the new ticks around the current fixed rate, and then it supplies the new range to the Voltz Vault, which will in effect do the rebalance, and effectively it triggers the function that Alex just talked about. So now that we've had a look at the rough architecture of the Voltz X Mellow system, or multi-vault system, let's have a quick look at the actual smart contract for the LP optimizer strategy. Now, let's have a quick overview of everything. There are several parameters which are supplied and settable in the strategy. Among those, you have something known as a sigma wad, a sigma parameter, a max possible lower bound, a proximity, and weights. Now, the sigma parameter is a concentration parameter which is used in the calculation of the ticks. So is the max possible lower bound. The proximity is used when checking the current fixed rate against a lower and an upper bound, and the weights are required to be able to tell the proportion of the funds that are to be deposited into each different Voltz vault, because this is a multi-vault system, and so you can distribute your liquidity across different pools within vaults. Those pools that Alex showed you earlier. You have several of these setters and getters, but the most important function would be, the first one would be the rebalance check. Now, this takes two arguments. It takes the index of the Voltz Vault that you're interested in. This could be an AETH lend or borrow, or a Lido or Rocket ETH pool, as described in the architecture. And the second argument is the current fixed rate. It takes the current fixed rate and it checks whether that current fixed rate falls within the specified lower and upper bound. And if we go back to the slides, the logic that is utilized for that is described here. The first line, if the current fixed rate falls within some lower bound plus a proximity parameter and an upper bound minus some proximity parameter, if it falls within that, then your position is fine and your capital is active, at which point the function returns false and there's no need for a rebalance. If the converse is true, that you are out of that range and you're violating the inequality, then it returns true and it effectively requires a rebalance. Now, the second most important role that this strategy has is computing those ticks themselves. And that's done within the rebalance ticks function, which takes, again, the index of the Voltz Vault, and it takes the current fixed rate as arguments. Going back to the slides, we see the logic which is implemented for determining the lower bound and the upper bound. So the lower bound of the new fixed rate is going to be the smaller of effectively a zero lower bound on the effectively the lower bound, and then the current fixed rate minus some standard deviation parameter. So that's going to be one of the options, and the smaller of this or the maximum lower bound, which is a parameter that's also settable. The upper fixed rate, that's going to be determined as a function of the lower fixed rate, plus 2 sigma, or sigma wad, which is defined as a parameter in the strategy. Going back to the actual contract now, looking at this function, it is the most important parts. It is only callable by an operator, and then the functionality where the new fixed lower bound it is executed here. So you determine what the new fixed lower bound is, and then from that you compute the upper bound, and you store these as the new fixed rates or lower and upper rates. And then what you do is you call the rebalance function on the Voltz Vault with index I, which you have passed as an argument in this function, and effectively emit a rebalance event. And the Voltz Vault will then carry out the two major steps which Alex has just described to effectively unwind your position from the current range that you're in, and then redeploy your the capital of the depositor in the newly computed range. Those are the main functionalities. The next biggest function effectively is the deposit callback, which, if we go back to the architecture diagram, we see that as a depositor deposits liquidity into the system, the root vault issues them their LP share tokens, which is in effect a way of showing that you have deposited liquidity. And then the RC20 vault is effectively this buffer or escrow, which keeps those deposits and then distributes them among the different vaults that we have. And this is based on the specified or on the pre-specified weights. If the weights are equally distributed, we'll go 4 ways into each of these specific vaults. And the deposit callback effectively triggers this this process. That summarizes the technical, or at least overview of the strategy. There are many different strategies that you can implement. It doesn't have to be an optimizer. You can use the strategy for different ways of effectively using inactive capital by maybe depositing some of that inactive capital in a different subvault. So these are completely customizable, and the most important part is that this is a modular setup where the strategy is decoupled from the main functionalities of the Voltz Vault itself, so that you can play around with having different strategies or make changes as needed. That's the end of it. We hope that has encouraged you, or that will encourage you to build on Voltz and with Voltz. And if you have any questions, we encourage you to reach out on the developer channels on Discord. The description will contain any of the links to the article and documentation for the code. And let's build the future of DeFi together. Thank you.